In this video, I want to talk about an important concept in electrical circuits, which is called the maximum power transfer. So let's just assume we have this resistive circuit or resistive network that contains a bunch of resistors and some independent and dependent sources. So far you have seen how we can use electric circuits techniques to come up with a Norton and Thevenin equivalent circuit of this whole network. But the concept of maximum power transfer talks about how we can choose our load resistor in such a way that the maximum amount of power possible is delivered to this load resistor. So to answer that question, let's just replace this resistive network with its Thevenin equivalent. So we have VTH and RTH here. And let's just write down the equation for the power that is being provided to this RL. So to get that, first we need to calculate the current that goes through this circuit now. So the current I is going to be equal to VTH divided by RTH plus RL. What is the power for RL? So I call it P of RL equals RL I squared, or it is RL multiplied by VTH squared over RTH plus RL squared, or I can write it a little bit nicely as RL over RTH plus RL squared multiplied by VTH squared. So this is the equation for the power that is being delivered or is being consumed by RL. So how can we maximize this? So in this equation, since we don't have any control over this resistive network, we basically don't have any control over VTH and RTH. So in this equation, VTH and RTH are both constant values, fixed values we don't have any control over. But for the load resistor, we have control over it. So let's just say, for example, you want to connect an audio amplifier to a subwoofer, right? So for the audio amplifier, you don't have any control over it. But for the subwoofer, you may have some options. So if you know what is the internal equivalent circuit for the amplifier, you may be able to choose RL or the subwoofer in such a way that the maximum power is being delivered to it. So how can we ensure that? The answer to that is we need to take derivatives of the power with respect to RL. So basically, if you remember from your math courses, if you have a function and you want to find the maximum or the minimum value for that function, you take the derivative with respect to the variable. So that is what we want to do here. We want to find the derivative of P of RL with respect to RL. So for this derivative, VTH is a constant value, so it stays the same as it was before. But for this part, we need to calculate the derivative because we have both RL in the numerator and the denominator. So you remember if you had, let's say, g of x as f of x over k of x, basically the derivative of g with respect to x would be f prime of x, k of x, minus f of x, k prime of x, and the prime is representing the derivative operation, divided by k of x squared. So we basically do the same thing here. We take the derivative of the numerator, we multiply it by the denominator, minus the derivative of the denominator multiplied by the numerator divided by the denominator squared. So we have the derivative of RL with respect to RL is 1. So we have 1 multiplied by RTH plus RL squared minus, what is the derivative of the denominator? It is going to be 2 multiplied by this term in the parentheses. So it is 2 multiplied by RTH plus RL multiplied by the numerator. So it is RL. The whole thing is divided by RTH plus RL squared. So it has already a power of 2, so it will be to the power of 4. So at the point of maximum or minimum, this thing equals 0. So we need to find RL. So this equation becomes 0. For this equation becoming 0, VTH cannot be 0, right? Because if VTH is 0, then basically there is no power. Also, the denominator is not important, because for this whole thing becoming 0, only the numerator needs to be 0. So that means that RTH plus RL squared minus 2 RTH plus RL multiplied by RL, this needs to be 0. So let's just see what is the condition for this to be 0. So let's just calculate this quadratic equation. This is going to be the RTH squared plus RL squared plus 2 RTH RL minus, we have 2 RTH RL, 2 RTH RL minus 2 RL squared equals 0. So as you can see, this and this are equal with opposite signs, so they cancel each other out. We have a positive RL squared, we have 2 negative RL squared too. So this one and this will also go away too. So we have RTH squared minus RL squared to be equal 0, which means that RTH should be equal to RL squared. So there are two cases for this to happen. One is if RTH plus RL equals 0, or RTH is negative RL. The second case is that when RTH minus RL equals 0, which means that RTH equals RL. So between these two cases, this one is not useful for us. Why? Because we are working with positive resistors. So for example, if RTH is 5, RL, or if RL is 5, that means that RTH needs to be negative 5, right? So this doesn't make sense for the circuits that we work with. But the second one makes sense, because it says that in order for this circuit to deliver the maximum power to this load resistance, RTH must be equal to RL. So that is the condition to have the maximum power transfer from the resistive circuit to the load resistance. So let's just go through these steps one more time. So first, we write the equation for RL's power. The power is going to be its current squared multiplied by the amount of resistance. So the current is VTH divided by RTH plus RL, because when we have RL connected between point A and B, we have RTH and RL to be in series. The current that goes through this circuit is calculated by Ohm's law, the voltage across the circuit divided by the whole amount of the resistor in the circuit. So here, since these two are in series, the total resistance is going to be RTH plus RL. So this VTH over RTH plus RL creates the current. We square it and then we multiply it by RL. As I said, in this equation, VTH and RTH are constant because we don't have access to the internal parts of the resistive circuit. What we have access to is only the terminals. And we know that how we can get from the two terminals following a several step procedure to calculate the Thevenin and Norton equivalent circuits, right? So now we want to have maximum power transferred to RL. So that is the requirement. To get that, we write the derivative of the power with respect to RL and make it equal to 0. So we can calculate RL in terms of RTH and possibly VTH. So this is the result of the derivative. We have the derivative of the numerator, which is 1 here, right? It is RL by itself, so its derivative is 1, multiplied by the denominator, minus the derivative of the denominator, it is 2 multiplied by RTH plus RL, by the numerator. The numerator here is RL only. And VTH squared is basically, since it's a constant value and it's not dependent on RL, we basically treat it as constant and we don't need to do anything with it. And then this thing is divided by the denominator squared. So it was RTH plus RL squared. So now it should be RTH plus RL to the 4th. So now what we need to do is that we need to make this derivative to be 0. And in order to have that, the numerator needs to be 0, or RTH plus RL squared needs to be equal to RL multiplied by 2 multiplied by RTH plus RL. As I said, there are two cases for this that can happen. We can have RL to be negative RTH, which is a pointless case for us because we don't have negative resistors here. So the other case and the valid case for us is for RL to be equal to RTH. So when we choose RL to be equal to RTH, we basically deliver the maximum power possible to RL. Anything below that or above that basically reduces the amount of power that is delivered to RL. So now you might ask, what is going to be the amount of power that will be delivered in this case? The answer to that is very simple. We had the equation for the power to be I squared or L, or it was VTH over RL plus RTH squared multiplied by RL. So now if we combine this with the equation that we found here, this one, RL equals RTH, the maximum power that is being delivered is VTH squared multiplied by RL divided by 2RL squared, or after simplification, it is VTH squared over 4RL. So that is the maximum power that can be delivered from the resistive circuit to the load resistance. In this video, we went over the concept of maximum power transfer. We saw how we can maximize the amount of power that a resistive circuit can deliver to a load resistor. And then we went through several steps to find out what that maximum power is.